all of you. In this class, I'll discuss about input and output impedances of current series feedback amplifier. Okay. First, let me draw the block diagram of current series feedback amplifier. Yes, it consists of amplifier of gain A, yes, another main circuit is feedback network of factor beta. Yes, see this is current series, means the sampling is current and the mixing is series mixing. As the sampling is current, we already know about the sampling circuits. Yes, RL, and this is IL, or you can write it as I0. So this is a circuit for current sampling. Okay. So to this feedback network, the current I0 is given as input. Then what is the amplifier input? As it is series mixing. Series mixing means the input must be a voltage source. Yes. Your feedback signal must mix with the Vs in series. So this is your Vf. As the input is voltage source, the feedback network output must be voltage. Okay. And as usual, this input is Vi. Input voltage is Vi. Now if you observe, yes, already we know about the current series feedback amplifier. In the current series feedback amplifier, the basic amplifier is trans-conductance amplifier. Okay, so let me explain how. What is the output of amplifier? Current. I didn't indicate any voltage. The current, and again the current is sampled. Okay, so the output is current. What is the input? Input is voltage. So what is this amplifier? Output is current and input is voltage. So, what is gain A? A is equal to output current by input voltage. Okay? Yes, current by voltage is nothing but trans-conductance. Why it is called trans? Trans is a word which relates input and output. Okay? Suppose if it is normal like II by Vi. So, that two II and Vi are related to the input. So, no need to use any trans. Suppose if it is I0 by V0, as the two parameters are related to the output, no need to use any trans. But if you see this, it is I0 by Vi. One parameter is the output parameter and another one is input parameter. That is the reason you have to use trans. Okay. So as this is conductance, yes, let me replace this A with Gm. Okay. So what type of amplifier it is? It is trans-conductance amplifier. Okay, so it is trans-conductance amplifier. Now, we'll find input and output impedances of this current series feedback amplifier. Yes, we know to find the input and output impedances, you must draw Thevenin's equivalent circuit of your current series feedback amplifier. Okay, so I'll draw the current series feedback amplifier. Thevenin's equivalent here. Yes. So input is voltage, Vs, Ri, and then exists mixing of feedback voltage. So in input side, you have to connect feedback voltage like this. What is this Vf? As the output of the amplifier is current, yes, see what is beta or what is Vf? Vf is equal to beta I naught. Okay, so here you have to write Vf as beta I naught. Okay, then what about output side? Output is current sampling. So you have a current source, that is GMVI. What is VR here? This is your VR. Okay, GMVI. In shunt, you have the output resistance R0, and in shunt, you have the load resistor RL. Okay, so now this current is I0 or IL. Okay, so this is the equivalent, Thevenin's equivalent circuit of your current series feedback amplifier. We know, suppose if you remove Vf is equal to beta I0, just short it, then what about the circuit? The circuit is nothing but the Thevenin's equivalent circuit of trans-conductance amplifier. Okay, but if you add this feedback, then it becomes current series feedback amplifier. Okay, so now let's see what is this input impedance. Okay, so now see here, after the addition of this feedback, this becomes feedback circuit. So that is the reason you have to mention, yes, RIF here. So what is RIF? RIF is Vs by II. Okay, what is II? The current in the input circuit is II. Okay, so now I'll keep adding. Input impedance. Okay, input impedance. Okay, so now as this is series mixing, yes, if you see the input, it is very easy to write KVL. Okay, so simply you write KVL. Yes, see the VI notation is like this. Yes, simply. Yes, what is Vs? Vs is Vi plus Vf. Simply. Yes, otherwise you write the elaborated KVL plus Vs. Okay, and the second terminal is minus Vi, and the second is minus Vf is equal to 0. Okay, so what is Vs? Vs is equal to Vi plus Vf. Okay, yes, now this is from input KVL. From input KVL. Now, yes, substitute Vf. What is Vf? Beta I naught. So to solve this, you need I naught. So what is I naught? So from output, yes, you must write I naught. See the output circuit here. This is the dependent current source. It is coming to this node like this. Okay. So and this current, yes, it comes to this node like this. And it is divided into this and this, these two parts. Okay. So now, what is the current through RL? I naught. Okay. We need that I naught. What is I naught now? The total current, GMVI into opposite resistance, current division formula simply, R naught by R naught plus RL. Okay. So now, see this. This is transconductance amplifier. Yes, in the transconductance amplifier, yes, in the previous videos, I already explained the code. What is that code? HH means input resistance is high and output resistance is also high. Okay, so if you take that as R0 is far greater than RL, so what you can do? You can neglect this RL compared to R0. Then you can cancel R0, R0. So what is I0? I0 is equal to simply GMVI. I0 is simply GMVI. Okay. So now substitute this I0 in Vs. So it implies Vs is equal to, yes, what is this? Vi plus beta into, what is I0? GMVI. Okay. GMVI. So take Vi common. So if you take Vi common, it is 1 plus beta GM. What is Vi? So if you observe here, it is Ii into Ri. So Ii into Ri of 1 plus beta Gm. Okay, yes. Now, what is RIF? Therefore, RIF is equal to, yes, input impedance with the feedback. RIF is equal to Vs by II. So, Vs by II. So, this is Vs and take this II in the denominator. You will get it as Ri of 1 plus Gm beta. Okay, so that is your feedback resistance or the resistance, input resistance with feedback. Okay, so this is your RIF. Okay, so what is the conclusion here? The conclusion is, yes, without feedback, the resistance is Ri, but with the feedback, the resistance of the transconductance amplifier is increased by a factor 1 plus Gm beta. Okay, so that is the conclusion. So, and now if you observe, for voltage series, the mixing is series. There also the input impedance is increased. And here also, as the mixing is series, yes, the input impedance is increased. So, what is the conclusion? With the series mixing, yes, the input impedance is increased. Okay. Now, let me find the output impedance. Okay. Output impedance. Okay. So, now for this output impedance, yes, remember one point. While finding the input impedance, you must start with input circuit. While finding the output impedance, you must start the derivation with the output circuit. Okay. So, now, what is this output circuit? See here. Yes. And another important point. In the voltage series circuit also I explained. What is that important point? While finding the output impedance, yes, if the input is voltage source, make it short and then disconnect the RL. If the input is current source, make it open, also disconnect your RL. Okay, so you do that. Yes, to find the output impedance, what you have to do? You have to short this Vs as the input is Vs. So simply short it. Yes, simply you short it. Okay. Yes, then you have to open this RL, disconnect the RL. Yes, simply you disconnect it. Okay. Then take this current as I. Okay. Then this voltage as V. Yes, this current as I. Okay. So, from this open circuit, the current coming into the circuit is I and the current going to the RL is I naught. Okay. So, what is I and I naught? Now, I is equal to minus I naught. Okay. Then here, assume a voltage V here, which is equal to the output voltage. No problem. Okay. Now, we'll go for output impedance. This I is coming to this node and then it gets divided like this. Yes. This and this, the green color arrows. Okay. So now I'll write KCL at that node. Okay. If you write the KCL, yes, then I is equal to, yes, this is, the resistance is R0 and the voltage across R0 is V. So what is the current through R0? V by R0. Fine. Okay. Then, yes, another current is like this, but here already there is a dependent current source which is coming like this. So, the KCL gives minus GMVR. Minus GMVR. Okay. So, yes. Now, what you have to replace? You have to replace your VI. Yes, VI, to replace VI, you have to use the input circuit. So, what is VI here? Yes, VI is, yes, we know from the input KVL, see this. So, Vs is equal to Vi plus Vf now. So, and as you are shorted Vs becomes 0. So, what is Vi? Vi is minus Vf. that is minus beta I naught. And I already told you, yes, I and I naught, I is equal to minus I naught. So you can write it as beta I. Fine. Now you substitute this in this expression. So it implies I is equal to V by R naught minus, yes, if you substitute beta I, Gm beta I. Fine. Yes. Now take, yes, this term this side and take I common. 1 plus Gm beta is equal to V by R naught. Okay. Then, yes, I forgot to indicate the R naught F. So what is R naught F here? This is your R naught F. Exactly at those open terminals. Okay. That R naught F formula is V by R. Fine. Okay. So now from this, your R naught F, that is V by I, yes, you just take this I to that, yes, then it becomes R naught of 1 plus Gm beta. Okay. So what is R naught F? R naught F is equal to R naught into 1 plus Gm beta. Okay. So, yes, in the absence of feedback, the output impedance of the transconductance amplifier is R naught. But when you include the feedback in the form of current series, so what happens to the output resistance? It gets increased by a factor 1 plus Gm beta. Okay. So now if you look at this total derivation, very simple derivation, yes, we got two conclusions. Input impedance increases with feedback and output impedance also increases with the feedback. Okay. So this is about input and output impedances of current series feedback amplifier. Okay. Thank you.
Thank you for watching this video. If you like this video, please don't forget to like, share and subscribe.